Hi everyone. So my name is Alex, and I'm a software engineer at developing ML software at Intel Ireland. So current topic, I will say its name in full. So it is Python interface for high-performance C++ library done the right way. So I will provide you some general thoughts about it and also their application to particular C++ library and its Python interface. So let's start with simple question. Why isn't native Python is used for everything, including high-performance computation? I guess it is obvious question, but just to remind, I can tell that Python interpreters are really slow, and it's actually feature of interpretability and scripting languages in general. And it allows us to write very high-level code in shortest time possible, but it is also a trade-off on performance of native Python code. So there is also some optimized interpreters like PyPy, but it is not near performance of compiled languages. So I guess many of Python programmers faced some moment of alignment when they realized how actually slow Python interpreter is. So my first anecdotal evidence for it, I gained it during exercising in competitive programming. So I restored one solution for competitive programming task for this talk, and I wrote this solution into languages. It's plain Python and C, and as you can see, Python has some performance increases in last versions. Also, PyPy interpreter works significantly better, but C is still far ahead, and with optimization flags to enable some native features of CPU architecture, it is just comically faster than Python by a few hundred of times. And there is also real evidence for it. So in a research paper ranking programming languages by energy efficiency, Python is shown to be 70 times slower and less energy efficient. So, but what is the main consequence of this performance behavior for broader Python ecosystem? It is reflected in high-level design and structure of code for mostly all Python frameworks. So they are designed in some similar way. So low-level building blocks are written in some compiled languages. Usually it is C or C++, but it might be others like Rust and so on. And there is some interoperability layer to enable some additional interfaces, including Python. And of course, there are few. There might be native APIs to get access to low-level building blocks. And examples for this is, most popular examples are OpenCV, TensorFlow, XGBoost, and many others. So, particular example in this talk is oneAPI data analytics library. It contains highly optimized building blocks for machine learning for all ML stages. It works on both ARM architecture and standard and usual x86. Also, it enables, in addition to CPUs, Intel GPUs, and it supports all computation modes. So it has streaming and distributed computational modes in addition to usual batch mode. And also, I will mention it is supported also on GPU. And it is built on top of other oneAPI libraries like TBB, threading building blocks for obviously threading, and MKL math kernel library. Also, it is part of few initiatives for accelerated computing like Unified Accelerate Foundation and oneAPI program made by Intel. And important note here, unlike most of Python frameworks where optimized low-level building blocks and Python bindings were started in development simultaneously, oneDAL initially started as separate library, and then it has gained few interfaces, and most important of them is Python. So general question: what is the purpose of Python interface for this kind of library? So there are two obvious objectives. Firstly, provide available speedup, because nobody will enable some additional dependencies in their workflow just to gain few percents of speedup in most cases. And second is achieving of widest possible adoption in ecosystem for this library, because what is the meaning of all these performance achievements if there is no actual user base to use it in the real world. So these two objectives, performance and ease of use, they are both important and should be in balance. As I previously said, Python interface for oneDAL evolved dramatically. It has 3 iterations of development and actually 3 final products. So first of all, it was simple buildings from C++ native interface to Python called PyDAL. Then it was deprecated and removed in favor of DAL for Py, which is more useful ML extension for existing Python ML ecosystem. And then it was improved and renamed into Intel extension for Scikit-learn, Scikit-learnex in short form. So first iteration is PyDAL. As I previously said, it is simple Python buildings using Swig tool to translate native C++ interfaces to Python. And because of its simplicity to implement these interface files, it fully covers oneDAL functionality. Also, there is important feature. It doesn't provide any helpers for end user and fully follow oneDAL internal workflow like it is done in C++. So there is a simple example for Swig tool. So Swig is abbreviature for simple wrapper and interface generator, and it is simple translator from C to Python to create some bindings for existing C++ interfaces. So this is PyDAL example, and if you remember previous two objectives, obviously you can understand the problem with this example. This is you don't need to read this in details. Just understand one important thing, which I will say later. So this is example for training and inference for simple linear regression model. And there is one problem, as I previously said. It doesn't provide meaningful API for end user. So there are custom handling of batch algorithm instance for linear regression. It sets some parameters and inputs on separate lines, and also some conversions between NumPy in the array and internal oneDAL numeric tables. And because with Python bindings are simple, there is no actual performance loss on this side, except some invisible losses in Python interpreter. And so it was decided to provide some meaningful extension for Python ML ecosystem. And this example was reduced, same example doing same thing was reduced to this simple code. So many of you, I guess many of you familiar with Scikit-learn. It is classical machine learning framework, and you can patch it with oneDAL kernels in two simple lines of code, or just Python module call. As a result of this patching, user workloads can simply be modified to existing user workflows, what is important. So DAL for Py is second generation of interface for oneDAL library, and there are few case specifics. So instead of simple Swig translator, there was Cython in use. I will explain what it is later. And this Cython code was generated by custom template generator, which reads oneDAL C++ interfaces and generates standard bindings with some handling of exceptions. And second specifics is monkey patching for Scikit-learn. It was shown in example, and also it was compliant with Scikit-learn Symmetrics API. So end user of Scikit-learn can enable this extension and do not bother about some numerical errors, some different workflow, and other non-standard issues, which they didn't face with stock Scikit-learn. So Cython is both a compiler and programming language. So Cython language is superset of Python and C. It allows to combine their power in extended interoperability and use both of them in same code. And also Cython compiler transforms Python code to C code with significant performance gain, and also it has significant ecosystem of Python frameworks around it. For example, NumPy, SciPy, Scikit-learn, many others. So there is example for Cython. So there is on left side there is header and implementation of simple arithmetic function, and lower there is some arithmetic function written in Python, and on right side there is Python code, and you can see it contains both imports from Python and C, and it allows to combine them in one code base, basically. So most important feature of Scikit-learn of DAL4Py is monkey patching. So it allows to, so monkey patching in Python is dynamic modification of class or model at runtime, and Python allows to modify basically everything at runtime. So you can patch some method of some class, replace method of object, and for DAL4Py it is replacement of machine learning estimators in Scikit-learn APIs. So on right side you can see there is actual replacement of linear regression, example for replacement of linear regression by DAL4Py. So it is simple reset of this property of model, attribute of a model. And after DAL4Py, there was Intel extension for Scikit-learn, sklearnex, and it was basically a superset of DAL4Py and additional functionality. So it added Pine-Bind 11 wrappers to adopt new DPC ++ interfaces of oneDAL. So DPC ++ is language which allows to, in simple terms, allows to use XPUs, and for example, it is mostly used in sklearnex to offload to Intel GPUs. So Pine-Bind 11 is header-only library, what enables interoperability between C++ and Python, and it unlike Python, it works with C++, and it allows to, it contains many helpers to work with C++ structures and classes. So, and also some numeric utilities to interact with NumPy and D arrays. So, as I previously said, Scikit-learnex introduced machine learning on Intel GPUs, and actually it is done pretty similarly to patching in terms of simplicity. So you just need to patch Scikit-learn as usual, and then import Scikit-learn instances. Like, for example, in this example, as we see, support vector machines classification and train test split utility will be patched. And basically, and then use config context to specify target offload to GPU. So there was, I often mentioned acceleration in my talk. So there is actual slide for this acceleration. So it is just sample data for mid-tier Xeon server CPU, but depending on case, on hardware, on task, and also algorithm parameters, speed up might be different, but it allows to achieve significant performance in some cases. So while working with Scikit-learnex, I encountered many challenges, and mostly all of them were related to integration into existing Python ML infrastructure. So, in order to support user workflows, it is required to support different data formats. So, Python NumPy, Pandas, sparse formats from SciPy. They are basic formats, but also there is requirement for specific data format for GPU in order to avoid transfers between host memory and GPU memory, because it kills most of performance gains on GPU. And also, even if written correctly, there are significant overheads in Python interface, because it is required for Scikit-learn. It was a requirement to enable same input and parameters validations like Scikit-learn did. So it was basically reusage of Scikit-learn function and utilities. And during this validation development of validation utilities, there were significant Python overheads in streaming computation mode. So Python interpreter overheads for inference on one sample of data was significant, and it kind of made real ML computations just like noise in terms of actual computation time. And also, there are broader challenge to comply with all Python ML ecosystem, because on top of Scikit-learn there are built many after machine learning frameworks, and they also have specific requirements for algorithmic results and so on. And also, because no low-level machine learning kernel is written in the same way, there is always a numeric bit-to-bit error in results. So actual results of Scikit-learn and Scikit-learn doesn't always match each other, and it is required to provide some testing infrastructure to ensure it is not a real problem, but just bit-to-bit difference. Okay, so Scikit-learn is available in CondaForge and Python package index. You can install it with simple commands like this. And that's all.
You monkey patching Scikit-learn, right? But I think, or I guess, Scikit-learn under the hood is also not written in Python. It's something binary. Is there a real performance boost anyway?
Do you mean, higher level instances of Scikit-learn are patched, like estimators, high level functions. Basically, validation utilities are same, because it is a requirement, and under hood, actual computations are replaced by oneDAL kernels. So in terms of Scikit-learn, computations are based on some third-party libraries like libsvm. They might be written in Python, and because they are not always written in optimal way with optimal tools, they are slow, especially, for example, SVM. Depending on hardware, you can achieve hundreds of times speedups.
Thanks.
Yeah. Thanks for the presentation, Alex. A small question. You know, I heard nowadays that the Rust language became more popular, and it allows to achieve performance that's compatible with C and C++ languages. So, and you told us that all these libraries like Scikit-learn and others are written in C++. What's the reason for this? Maybe it makes sense to just change and language to Rust. Do you have any opinion on that?
Rust received hype very recently, and oneDAL is much older than it. So I guess it is partially a question of legacy code and also enabling of new languages, but in general terms, moving to Rust, I don't think moving to Rust and writing significant architecture around it for writing kind of same of ML library code will receive higher gains than writing in plain C++. And I guess in general it is a question of moving to new tool, and it is not performant enough to just took it and replace it.
Thanks.
Any more questions?
Slowly moving this way. Instead of Python, we can use borders. Piece by piece, it's moving this way.
Okay. Thank you so much, guys. Thank you. Thank you, Alex.